Following video is a part of mini project submitted by our group for data structures using Python, year 1 sem 2nd of Data Science 2024, Kathmandu University. We have chosen our project topic to be Hoffman's algorithm, where we will be talking about its origins, mechanism, application, and implementation in Python. Today, we are going to dive into Hoffman coding, a fascinating and fundamental algorithm that plays a crucial role in how we compress data every day. We will start by understanding its origins and what problem it was designed to solve, essentially how to make our digital files smaller without losing any information. Then we will peel back to the layers to see how Hoffman coding actually works. We will explore its clever step-by-step process of assigning unique shorter codes to frequently used characters and longer codes to less common ones. This is where we will really see the magic of its efficiency. Finally, to bring it all to life, we will have a practical demonstration in Python. You will see the algorithm in action, transferring a piece of text into its compressed form, and we will compare the original size to the compressed size to appreciate the problem of this ingenious algorithm.
Algorithm. So let's talk where this algorithm came from. Here we have a picture of David A. Hoffman, who at that time was a graduate student at MIT. In 1952, he was assigned term paper by Professor Robert N. M. Pano. His paper was titled A Method for Construction of Minimum Redundancy Code, and using this algorithm outperformed the Pano-Shannon method, which is out of scope for this video. He made use of frequency sorted binary trees, thus resulting in lossless encoding and most importantly compression of data while transfer. So for example, we need to compress a text file, then we will need to create a table with each character and its frequency of occurrence and feed it to our algorithm as input for encoding. Our goal is to assign binary codes to each of those characters such that there is no loss of data while decoding. Also, we need to assign shorter binary codes to more frequent symbols and longer binary codes to less frequent ones. We will be using binary search trees and priority queue for this algorithm. The priority will be assigned according to the frequency of characters, which is how we get shorter codes for less and longer code for more frequent characters. The algorithm is greedy and guarantees a minimum length prefix tree encoding for separate symbol encoding. The time complexity is O over n.
So here we have a table containing characters and their frequencies. Let's try and encode these characters using the Hoffman's algorithm. We push all our elements into a priority queue. The priority is assigned according to the frequency of the elements. Our smallest priority elements are B and C as shown in the table. After taking them out of the queue, we create a new parent node containing some of their frequencies, that is 8, and add it back into the queue. After repeating this step until only one element remains in the queue, which is root of the new Hoffman tree we just created, we get the following binary tree. Traversing through the tree from root to leaf, we assign 0 to the left and 1 to the right nodes. The final result is this table. Now we have successfully encoded all of our characters according to the Hoffman algorithm.
Now, let's discuss some applications of Hoffman's algorithm. The first one is lossless data compression. Hoffman's algorithm is a cornerstone technique for efficiently compressing data without information loss. Second is transmission. It increases storage capacity and transmission speed in many digital systems and networks. The third one is cryptography and error detection. It forms the basis for certain encoding and decoding processes. Now we will be explaining our algorithm as well as using an example to demonstrate the encoding process. The first step of our algorithm is to create a leaf node for each of characters. We also need to put all of them into a priority queue in the order of their frequency. In the next step, we remove two nodes from the queue in order of their priority. Then we create a new parent node containing the sum of nodes and put this node into the queue. This process is to be repeated until only one node remains in the priority queue, which is root of Hoffman's tree we just created. For encoding, we assign 0 for the left and 1 for the right branch as we traverse from the root to leaf nodes.
So for the last part of our presentation, we would like to show the implementation of this algorithm in Python. So this is the implementation of Hoffman's algorithm in Python, and, and this is the following result that we obtained.